Welcome to Real-Time Streaming Architecture. I'm Ernest Russell, Technical Product Marketing Manager for Limelight. Today on the agenda, we have real-time streaming common architectures, mesh architecture, multi-point conferencing unit architecture, selective forwarding unit architecture, and then Limelight real-time streaming architecture. Originally, WebRTC was developed for real-time video conferencing using browser-to-browser connections. Today, I'll introduce you to three of the most common WebRTC architectures. Mesh, where all of the clients are directly connected via web browsers. MCU, or multi-point control unit, where a central server processes all video streams and sends back a combined video stream. And SFU, selective forwarding unit, which receives all video streams and forwards them to clients as needed. Mesh is one of the most common architectures for multi-party video calls. In a full mesh network, each participant establishes a two-way connection with every other peer on the call. No server is needed for this architecture, making it a relatively inexpensive option. The downside to using full mesh is that as the number of participants increase, CPU and network bandwidth increases. Network bandwidth is usually the limiting factor in a full mesh network. In a mesh network, every client has a direct connection. In this example, with 4 clients, each client will need to manage 6 connections, or 3 two-way connections. You can see how this can get messy fairly quickly. Mesh was one of the initial implementations of WebRTC. Used for video conferencing between small groups, a peer-in is one example of WebRTC video conferencing in an app. In this architecture, each user will need to send its media to all other users in the session, as well as receive all the media from each of those streams. Most video conferencing apps that use the mesh architecture are limited to only 12 concurrent video users. In an MCU architecture, a central server does the heavy lifting, reducing the burden on the clients. An MCU requires a high CPU or compute power and also high bandwidth to process user requests in real time and forward the streams to each user. An MCU server receives the video stream from each participant, tiles the decoded frames with the streams from all participants, and then encodes the tiled video to send back to each participant. Using an MCU architecture will greatly reduce the number of connections and compute resources needed for each client. However, it introduces a single point of failure with an MCU server going down. This example shows an MCU architecture with 4 participants requiring 2 connections each. BlueJeans is an example of a WebRTC application that uses an MCU architecture. All users connect to a central BlueJeans server, which tiles the video and sends back a combined feed. BlueJeans also uses data channels to add collaborative features like whiteboard and annotation. Most video conferencing apps that use the MCU architecture are limited to only 25 concurrent video users. One common way to scale real-time streaming is to use selective forwarding units, or SFU. An SFU will receive the broadcast in real time and forward the broadcast to subscribers. As the name implies, the selective forwarding unit will receive all media streams and have some intelligence to determine what streams to forward. The additional latency of the SFU is minimal because it will not buffer any incoming video, only forward the video according to its rule set. Using selective forwarding unit will reduce the total number of connections needed for each peer. Participants can request the stream they want to view at a bit rate that is appropriate for their internet connection. Participants with a slower connection will be served a stream with a lower resolution or bit rate. Peers do not have direct connections to each other, only to the SFU. Google Hangouts is an example of an application that uses the SFU architecture. The layout is referred to as Magic Square, where the loudest speaker becomes the largest image. A selective forwarding unit doesn't process video, but rather routes it to everyone who needs it. Each browser sends its media to the SFU, which then forwards that media to all other participants. Most video conferencing applications that use the SFU architecture are limited to 25 concurrent video users. Mesh architecture and multi-point conferencing units are not very scalable. This is a big reason why people say WebRTC won't scale. Let's talk about how we can scale real-time streaming. Since real-time streaming uses UDP, latency across long distances is low, under a second. Edge servers are for helping scale and reduce latency for fallback protocols. For more on fallback protocols, watch my presentation on RTS reliability. So here, instead of having a central origin server delivering globally, we want to have multiple SFUs, or edge servers, placed strategically in multiple POPs globally. Let's take a look at what's under the hood. We've partnered with Red 5 to deliver and scale WebRTC. One of the advantages of using Red 5 are its clustering and autoscale capabilities. The autoscale feature allows Limelight RTS to scale out quickly for large events or spikes in viewer traffic. It also helps us optimize operation costs by being able to scale in when edge servers are no longer needed. For ingest, we recommend that a customer feed 2 ingest servers in 2 separate regions. This helps with redundancy in case one ingest is lost. The Stream Manager is a central part of our architecture. It monitors the edge nodes. It collects stream statistics and performs autoscaling based on a predefined set of rules. It also provides REST services for operations to send API calls. The edge servers are where the viewers connect to view the media stream in real time. Edge servers are running Red 5 Pro software to transmux and distribute these streams. More edge servers can be added to support additional viewers. Here you'll see, starting on the left, are redundant ingests with seamless failover from primary to backup with automatic failback. So our customer would ingest an RTMP in single or multiple bit rates. Our customers will receive that stream in under a second. If WebRTC cannot be played, output stream will default to RTMP or transmux to HLS, but it can still take advantage of adaptive bitrate, ABR. Also, we can deliver WebRTC via TCP when firewalls block UDP traffic. Now let's talk about Limelight RTS features. Here on the left, we have our global footprint with initial deployment of RTS POPs, including North America, EMEA, and APAC. We'll be able to add more edge servers to scale as needed. For security, customers can restrict access to their live streams using slot-specific access control list, geo-blocking. They can also use CORS, or cross-origin resource sharing, to make sure their traffic is coming from approved domains. Also, MediaVault and SSL are supported. The protocols used in WebRTC, or our version of real-time streaming, is VP8, HLS, RTSP, and RTMP. The codec is H.264. Real-time streaming supports adaptive bitrate streaming, but requires the customer to send multiple bit rates. They can also send custom bit rates as their needs require. Analytics. Support will monitor the servers with Zabbix. Basic customer analytics will be available via control, and more detailed third-party analytics are being developed by an outside company, Nice People at Work. For captioning, real-time streaming does not currently include a method for captioning. Since this content is live, the client will have to use a third party to develop and provide live captions. Unlimited viewer. The initial build-out will include 4 edge servers and 3 POPs. within 3 regions for a total of 36 edges and over 100,000 connections. Viewers joining after the connection limit will receive an error message. Transcoding. The initial version of RTS will transmux only. Customers will be responsible for transcoding and providing the different resolutions and bit rates they want for adaptive streaming. Digital rights management, or DRM. DRM will not be available in the initial product. DRM is not currently part of the WebRTC specification. That concludes my presentation on real-time streaming architecture. Thanks.